This is the second lecture in chapter 6, and it's a continuation of our look at ionic bonding and covalent bonding. In this lecture, we're going to look primarily at ionic bonds and at metallic bonds, which we haven't really talked much about yet. So ionic bonds, remember, they exist between oppositely charged ions, and those ions are usually a metal and a nonmetal, or sometimes a metal and a nonmetal polyatomic anion. Metals always form positive ions. Nonmetals always form negative ions. And when those oppositely charged ions come into close proximity to one another, it causes an attraction between the opposite charges. And what happens is we get this buildup of ions that form a really predictable pattern. And so let's say the red are all positive ions and the blue are all negative. So we get this, what's basically called a lattice or a crystal structure, where we have positive ions surrounded on each side by negative ions and negative ions surrounded on each side by positive ions. And we end up with this very predictable crystalline structure that looks something like this picture at the bottom. You can see how that formation takes place if you look at the electron dot notation over here. We've got a sodium ion as an example, so a metal from group 1. It gives away its one valence electron to chlorine, which is a group 17 halogen. And when the chlorine gets that electron, both ions achieve noble gas configuration. And they also, if they are near enough to one another, they also share this electron cloud, or they don't share it, rather chlorine has the electron cloud, but there is an overall electron cloud around each, kind of loose moving cloud, that is this in a noble gas or an octet formation. So these bonds tend to be fairly tight, and that attraction is pretty hard to break up. As a result of that bond and the fact that the attraction between positive and negative ions is so tight, the properties of ionic compounds exhibit or represent that strength in bond. So because of the fact that they are very strongly attracted to one another, the ionic bonds don't easily break up. What that means in terms of observable or measurable properties is that ionic bonds have very high melting and boiling points. The surrounding atoms, so if you have, say, a compound of sodium chloride, we have lots and lots and lots and lots of individual sodium chlorides, and they're all together in this huge crystalline structure. It's hard to break up the bond between individual sodiums and individual chlorides, but it's also hard to break up the bond between individual sodium chlorides and the nearby sodium chlorides. Because that bond is difficult to break, it takes a very high temperature to get from solid to liquid, which is your melting point, or from liquid to gas, which is our boiling point. We have to exert a lot of energy, generally in the form of heat in this example, in order to change from one phase to another. Ionic compounds are also very brittle and very hard. They tend to shatter into fairly jagged pieces. And the reason for that is, again, when you have this lattice structure, let me do another lattice here really quickly. When you have this lattice structure, it's difficult to break the bonds between the individual layers of the lattice, right? So we have 1 layer, 2 layers, 3 layers. It's hard to break the bonds between each layer, just as it's hard to break the bonds from side to side within a layer. And so when force is exerted, there has to be a lot of force in order to get this to break at all. And when it does, it tends to break in these kind of jagged patterns. Other common properties are electrical conductivity. Because ionic compounds are made up of charges, they therefore conduct electricity, which is also a charged form of energy. and they generally have pretty high heat conductivity. I guess high is a relative term. They have higher heat conductivity than molecular compounds do. I'll say that. So molecular compounds are just the opposite. They have low melting and boiling points. They tend to be fairly easy to break apart, so they tend to be softer or more pliable, and they do not conduct electricity well at all because of the fact that their bonds are easier relatively to break up. So we're going to talk about a new type of bonding that we really haven't looked at yet, and this is called metallic bonding. Metallic bonding is an attraction that exists between atoms of the same type of metal. This is only in metals, hence the name metallic, and it's metal within the same element. So we're dealing with gold and gold, or silver and silver. We're not dealing with bonding between gold and silver because that doesn't happen. So metallic bonding is really interesting because we have these nuclei. Let's say we're dealing with, I don't know, magnesium, why not? And we have these outer valence shells that are empty, right? Magnesium is a group 2 metal, so it only has 2 valence electrons, and it has a lot, therefore, of empty electron cloud space. So when there's a quantity of magnesium around other magnesium, which happens in nature, right? If there's a pocket, if there's one magnesium atom, there's likely to be more. What happens is the electrons that are technically assigned, I guess, or present in each atom, as they're moving around in the electron cloud of that particular atom, elements of the same type tend to be near one another, and their electron clouds tend to overlap because there's such a large vacancy. There's not a lot of repulsive force between electrons of each atom. And what happens as a result of that overlap is these electrons are pretty free to kind of move and orbit and rotate in all kinds of shapes and directions, and so they have a lot of freedom between atom to atom, and that freedom and that overlap creates what's called an electron sea. It's not a highly structured system or a highly structured shape, but it is a very stable state of being, and it does allow for the elements to have a fairly low energy level overall. Properties that result from metallic bonds are very high electrical and thermal conductivity. So again, we're looking at the movement of energy. Electrical energy is charged energy, and because we're dealing with metals, which are charged, right, they have electrons, and those electrons are moving fairly fluidly. They conduct electricity very well. They also conduct heat. They pass heat from atom to atom very well. It's interesting because the electron sea absorbs energy, which you saw earlier on this year when we looked at the different flame tests, right? As we added heat energy, the metals would absorb it, and then you would see it reflected back in the form of different flames and colors as the electrons were excited and then dropped back down. And metals all have the ability to absorb that energy from both heat and from light, and then to reflect it back. So they absorb energy, the electrons jump up to a new energy level, but then they very quickly drop back down, and so we get this light being released, and you can see that in different colors. Because of that release of light energy, they're also very, very shiny. So you see that light being reflected. That's a quality called luster. So metals tend to be highly lustrous. The fluidity of the electron sea also enables metals to be both malleable and ductile, which means they can go from being a fairly ball-shaped or rock-shaped body of metal, and it can be pounded out flat, or it can be bent into a wire. It can be bent into all kinds of shapes, which are characteristic properties of metals. Metals vary quite impressively, actually, in their bond strength because there are such a huge variety of metals. The majority of the elements in the periodic table, as you know, are metals. And so their bond strength is very, very different from one to another. There's not a huge level of predictability or trend within the table. But the amount of energy that's required to turn this metal from a solid into a liquid and then quickly into a gas, which is called vaporization. The amount of energy that's required to do that is called the enthalpy of vaporization. So enthalpy is another term for the movement of energy or the amount of energy present. So that will do it for our look at ionic and metallic bonds and the properties of the three kinds of bonds that we have talked about this chapter. So please bring in 2 or 3 discussion questions and write your summary, and I will see you soon. Thank you.